Good morning, everyone. I am Nandini, and along with my teammates Tanush and Harita, we are presenting our project on image captioning using deep learning encoder-decoder model. This project focuses on building an intelligent system that can look at an image and automatically generate a meaningful caption in natural language. This combines concepts from both computer vision and natural language processing, which makes the project both challenging and exciting. To start with, image captioning simply means generating text descriptions from images. As shown in the slide, this task merges two major fields: computer vision, which helps extract information from the image, and natural language processing, which allows the system to produce grammatically meaningful sentences. This technology has many applications, helping visually impaired individuals understand their surroundings, auto-captioning photos on social media, enhancing e-commerce product search, supporting autonomous systems that rely on scene understanding. For our model, we use the COCO 2017 dataset, which contains thousands of images and 5 human-written captions per image. The main objectives of our project are listed here. First, we aimed to build a complete end-to-end image captioning pipeline. This includes dataset filtering, pre-processing, feature extraction, and model design. Next, we wanted to design a reliable sequence model that could generate captions word by word. We then trained an encoder-decoder architecture and evaluated how well it performed on unseen images. Finally, our goal was to produce captions that look natural, meaningful, and human-like. In this slide, we provide an overview of the COCO 2017 dataset. This dataset contains over 120,000 images, each annotated with object instances and multiple captions. Two big challenges we faced with this dataset were its very large size, which requires heavy computation, the complex annotation structure stored in JSON files. These challenges forced us to carefully plan how much data we could use during training. First, we loaded the instances, trained 2017 JSON file using the PyCoco tools library. From this, we retrieved the category names, category IDs, and image IDs. Since the COCO dataset is very large, we applied dataset reduction to make training faster. We selected only the specific categories that were relevant for our project and filtered the dataset based on those categories. Finally, we visually checked some of the filtered images to make sure the data was correct before moving on to pre-processing. With that, I will now hand over the presentation to Danush. Thank you.
Now I will explain the pre-processing pipeline that we used in our project. Pre-processing is an important step because both the images and captions need to be cleaned and prepared before training the model. We divided this into two main parts: image preprocessing and caption preprocessing. For image preprocessing, we kept it simple. Each image was resized to a fixed shape, then normalized so that pixel values are in a proper range. After that, the images were passed to the feature extractor model to generate feature vectors. Next, we have caption preprocessing. Here we followed a clear sequence of steps. First, we tokenized each caption, which means splitting it into separate words. Then, we cleaned the captions by removing any unwanted characters. After that, we added special tokens, like is less than start, is greater than, and is less than end, is greater than, so the model knows where a sentence begins and ends. Once this was done, all the words in the captions were converted into numerical sequences, because the model can only understand numbers, not text. After processing all captions, we created a vocabulary of unique words from the entire dataset. This vocabulary is used by the model to map each number back to a word during caption generation. So overall, Pre-processing prepares both the images and captions in a structured format, making it easier for the model to learn and generate accurate captions. For this slide, I will explain the overall model architecture we used for our image captioning system, which follows an encoder-decoder structure. The model has three main stages. The first stage is the encoder, where we use a pre-trained Xception CNN model. This encoder takes an input image and extracts a 2048 dimensional feature vector. These features represent the important visual information in the image. The second stage is the sequence processor. Here, we convert the caption words into word embeddings, and we also project the image vector into the same embedding dimension. This helps the model combine visual information and text in a meaningful way. The final stage is the decoder. We use a by LSTM to generate the caption one word at a time. The decoder takes both the image features and the previous words to predict the next word. At the end, a dense layer outputs a probability distribution across all the words in the vocabulary. So overall, the encoder understands the image. The sequence processor aligns the text and image features, and the decoder uses this information to generate a complete caption. We use the Xception model as our CNN feature extractor, but we removed its top classification layer. This allows the model to focus only on extracting important visual features from the image instead of predicting classes. The encoder takes each image and converts it into a 2048 dimensional vector. This vector represents the global features of the image, things like shapes, textures, and objects. We also stored these extracted features so that our training process became much faster because we didn't have to run the CNN again for every training step. The final output of the encoder has the shape, batch size, 2048. We chose the Xception model because it is fast, lightweight, and highly accurate in feature extraction. It gives strong performance without requiring too much computation, which made it a good fit for our project. For the decoder part of our model, we use a bidirectional LSTM. The decoder takes two main inputs, the word embeddings from the caption and the projected image vector extracted by the encoder. The bi-LSTM helps the model understand both forward and backward context, which improves the quality of the generated sentences. During training, we also use teacher forcing, where the correct previous word is passed to the model to help it learn faster and generate accurate captions. At each step, the decoder predicts the next word in the sequence, and this continues until the is less than and is greater than token is reached, forming the final caption for the image. With this, I would now like to hand over the presentation to Haritha. Thank you.
For the training phase, we used a very standard setup for sequence generation models. Our loss function was sparse categorical cross-entropy, which works well for predicting the next word in a sentence. The optimizer we used was Atom, because it is stable and efficient for deep learning tasks. We also created a batch generator, which prepared input and output sequences from the captions. This allowed the model to learn step by step, predicting each next word based on the previous ones. During training, the model learns from two main sources: the image features extracted by the encoder and the previous words in the caption. Combining both helps the model generate accurate and meaningful captions. We did face some challenges, mainly memory usage, a very large vocabulary, and slow training on CPU. But by optimizing the data and reducing the dataset size, we were able to train the model successfully. For the results of our project, we first tested how well the model understood the images and the captions provided in the dataset. On the left, you can see an example where we loaded an image with key points. This step was mainly used to visualize how objects and their positions are detected in the dataset. It helped us understand the structure of the COCO images and how the annotations are organized. In the center, we have images loaded along with their respective human-written captions from the dataset. These captions gave the model the correct examples to learn from. By looking at these captions, the model builds its vocabulary and learns patterns in sentence structure, such as how objects, actions, and surroundings are described. Finally, on the right side, we have our main output, the final image with the caption generated by our model. Here, the model successfully identifies that the image contains a baseball player throwing a ball on the field and forms a meaningful caption for it. This shows that the encoder-decoder architecture was able to understand the image features and generate a sentence that is relevant and grammatically correct. Overall, the results show that the model can recognize objects, understand context, and generate captions that closely match the content of the image. This demonstrates that our approach works effectively for image captioning tasks. In this slide, we highlight the main challenges we faced during the project. The first challenge was the complex COCO annotation JSON. It contains a lot of nested information, so extracting categories, captions, and image IDs required careful handling. The second challenge was that the dataset is computationally expensive. COCO has thousands of high-quality images, so processing and training on them takes a lot of time and memory. Another issue was balancing dataset quality versus size. Using too many images slowed down training, but using too few reduced accuracy, so we had to find the right balance. We also experienced long training times, especially because LSTM models process data sequentially, which makes training slower compared to newer architectures. And finally, managing OOV, out of vocabulary words, was difficult because some captions contain rare words that don't appear often enough to include in the vocabulary. Overall, overcoming these challenges helped us optimize our model and improve the final results. To conclude our project, we successfully built a complete image captioning pipeline from start to finish. We implemented an encoder-decoder model using the Xception network for feature extraction and a LSTM for generating captions. Our model was able to produce meaningful and descriptive captions for new images, showing that it understood both the visual features and the language patterns. By reducing the dataset and optimizing the training process, we were able to work efficiently, even with limited resources. Overall, this project gave us a strong foundation for future work, such as adding attention mechanisms, using transformer models, or extending it to real-time applications. In summary, our project successfully demonstrated how an encoder-decoder model can generate meaningful captions by combining image features with language understanding. This work gives us a strong foundation to build more advanced captioning systems in the future. Thank you for your time and attention.